Hello, my name is Amber Fong from the Advanced Power and Energy Program at the University of California, Irvine. I will be presenting on my research on renewable hydrogen production pathways from biomass via anaerobic digestion for California. Here's a quick outline of what I'll be going over. In California, transportation sector contributes about 40% to the state's overall greenhouse gas emissions. 70% of those transportation emissions come from the light-duty sector. So there is a great emphasis in the state to reduce emissions from this sector through encouraging the adoption of zero-emission vehicles, such as battery electric and fuel cell electric vehicles. Alongside expansion of these vehicles in the state, there must be a corresponding expansion in their infrastructures. The goal of this particular research I'm presenting is to establish the optimal siting and siting of facilities for biomass anaerobic digestion, carbon neutral hydrogen pathways for California, given resource and conversion pathway constraints. I'll be going over some background on this research. In California, there are 62 hydrogen refueling stations. 41 of them are open for business for light-duty retail, and 21 are still under construction. In the state, there has been an emphasis not only on producing hydrogen fuel, but also producing renewable hydrogen fuel. California Senate Bill 1505 requires by law that 1/3 of the hydrogen fuel sold for light-duty use must be renewable. This is defined as either being produced via electrolytic hydrogen from renewable electricity or being produced from renewable natural gas. Also, the low carbon fuel standard program in the state requires that fuel distributors have 40% renewable hydrogen across their networks in order to qualify for their hydrogen refueling infrastructure programs. Currently in the state, the fuel is 39% renewable across the entire network. As I mentioned earlier, one way to produce renewable hydrogen fuel is to derive it from renewable natural gas. And one way to produce renewable natural gas is from anaerobic digestion. Anaerobic digestion is a series of biological processes through which microorganisms decompose biomass in the absence of oxygen. The resulting biogas is about 60% methane and 40% CO2. In the scope of this research, I utilized Geographic information system software. This is a helpful tool that visualizes, manages, and analyzes geographic data. This allows for higher spatial detail and analyses for research. This particular tool is used in a wide scope of fields, including public health and urban planning. But in the scope of energy systems modeling, it's been used also in regards to hydrogen infrastructure planning. Two examples of this include the STREET tool, which was developed by the Advanced Power and Energy Program, and also the California Hydrogen Infrastructure Tool, or CHIT, which was developed by the California Air Resources Board. With regards to this particular research, GIS is used to account for spatially dependent variables, in this case, the transportation portions of a fuel supply chain. I'll be moving on to the methodology. Since I'm putting an emphasis on the spatial component of the fuel supply chain, I need to gather spatial data sets. Here are where those data sets are coming from. For the feedstocks, the spatial data sets come from the Department of Energy's Billion Ton Report, and three categories I focused on were municipal solid waste, food waste, and animal manures. The spatial data set I used for the anaerobic digestion candidate sites came from a zoning data set from the US Geological Survey. And for the hydrogen refueling stations, the data set comprises of the current state network, the open and under construction stations, and then in addition to that, a parsed down data set of gas stations, which has been narrowed down according to the CHIT tool, what it determined as high priority areas for hydrogen stations. In addition to these spatial data sets, There are two other variables, and that is the conversion technology for biogas to hydrogen. And the ones I considered here are steam methane reformation and trigeneration fuel cell. Trigeneration fuel cell is a technology that is a high temperature fuel cell that can intake natural gas and through internal reforming produce hydrogen. Here is a summary of the emission and cost factors I used in the supply chain analysis. Most of these factors have to do with the digestion process or the transportation process, either of the biomass or of the hydrogen fuel. Now that I have all my spatial data sets and all my emission and cost factors, I can go ahead and calculate the spatial dependent variables in GIS. And there are two transportation legs that I'm considering here. The first is the biomass, transportation of biomass to the digestion facilities, and the second is the transportation of the produced renewable hydrogen to hydrogen stations. In the first transportation leg, the number of anaerobic digestion facilities is unknown, so that is a variable that is spanned. There are 12 scenarios spanned from 1 to 100 facilities. And the output of the facility output from that goes into the second transportation scenario, in which the hydrogen is taken from those digestion facilities to stations. Since there are 12 digestion facility scenarios and 3 feedstocks, that's a total of 36 scenarios that were considered. Here is a visual representation of those transportation steps. This is the first one, in which calculating an origin destination matrix between the feedstock and the candidate sites results in a siting of anaerobic digestion facilities. And in the second transportation step, there is an origin destination matrix calculated to transport that produced hydrogen to stations. And this is just one particular result for one of the 36 scenarios. And here are some example results. Here is a summary table of the produced hydrogen from the 3 different feedstocks considered, from the amount of biomass to the natural gas production to the renewable hydrogen production. Note that the renewable hydrogen production numbers are in kilograms of hydrogen per day. To put these numbers into scope, the Air Resources Board projects that hydrogen throughput in the state exceeded 3.5 million kilograms in the year 2019, which is approximately 9,600 kilograms per day. And one of the larger production facilities in the state, this is a steam methane reformation plant in Wilmington that produces about 4,000 kilograms of hydrogen per day. Here are cost and emission curves just for the manure feedstock scenarios. On the left-hand side is the emissions graph. On the right-hand side is the cost graph. Across the top is for the steam methane reformation scenarios, and across the bottom is for the trigeneration fuel cell scenarios. As you can see on the right, the emissions are minimized at 1 facility cited, but cost is minimized on the left-hand side at around 5 to 10 facilities cited. Given these two results, and given that the goal is to minimize emissions and costs, here is the final graphical result, which is citing 5 facilities across all 3 biomass feedstocks. The municipal solid waste and food waste results were the same, so they are the same legend item in this graph. In conclusion, building 5 anaerobic digestion facilities minimizes the greenhouse gas emissions for this biomass, anaerobic digestion, carbon neutral hydrogen fuel production pathway. Second, there is a sufficient amount of biomass in California available to produce a significant amount of carbon neutral hydrogen fuel for the state. This is particularly important as the state projects that there is going to be a higher demand for fuel in the future. And lastly, steam methane reformation is less expensive than trigeneration fuel cell for producing hydrogen, given that there are no additional economic incentives or additional pricing structures in place. This is important for policy formulation if policymakers have a goal of encouraging trigeneration fuel cell use in the future. I would like to thank the following people who were crucial to this research. First is my advisor, Professor Scott Samuelson, and then also Dr. Brendan Schaefer, Dr. Kirsty Manlick, and Jane Sukup contributed a lot to the progress of this research. Thank you very much.